Log on, tune in, find out. Another good idea from Cambridge.
I'm Prof from Padova, who will speak on convex decay of entropy for interactive systems.
Okay, thank you very much. Thanks to the organizer for the kind invitation. So my talk will mostly be about functional inequalities, those inequalities that have been mentioned by Prasad et al. In his Monday's talk in a discrete setting. And what I will be saying is mostly contained in those papers. I just wanted to mention my collaborators, Pietro Caputo, Gustavo Posta, and my former student, Severin Boudou. And I mean, the few new results that I will present are still unpublished, and they are in collaboration with Gustavo Posta. So, what is all this about? This is mainly about convergence to equilibrium for Markov chains. And so I suppose I have a Markov chain, ergodic. I take a continuous time Markov chain, say the state space is finite or countable. And let me denote by pi the stationary measure of this chain. And I denote by St, the semigroup e to the TL. So this is, of course, a time homogeneous Markov chain. So L is the generator. And if mu denotes probability on X, I denote by mu St the law at time t of the chain that starts from distribution mu at time 0. So this is just standard notation. Now, what one is interested about is the convergence to the equilibrium of this law. So how fast mu St converges to the invariant measure pi as t goes to infinity. So maybe the most natural mode of convergence to equilibrium is in total variation. So if I defined as usual the total variation distance between two probability measures, one very natural question is to ask what is the rate of convergence of mu St to pi in total variation. Now, as a matter of fact, there are several ways of obtaining estimates for the rate of convergence to 0 of this quantity, and it is typically easier to study first other modes of convergence rather than total variation directly, and then to extract from those modes of convergence information about total variation. So I will briefly mention other modes of convergence. So just to say some notation, I will denote by pi of f with a square bracket, just the mean of f with respect to equilibrium, with respect to pi. So what is the L2 convergence? So remember, St is a semigroup, so it's functional, is a linear operator acting on function, so I can think to it as an operator acting in L2 of the invariant measure. And of course also the pi can be thought of as an operator, just maps a function to a constant function which is constantly equal to its expectation. So I can consider the difference between these two operators and find the operator norm of this operator in the L2 space. So this is the definition of the operator norm. So this object can actually be used to give upper estimates for the total variation, and it is known that this inequality holds. So suppose I want to know the distance in total variation of St of of an initial measure, but something uniform in the initial measure. So I can take a delta x is just a direct measure at x, and I take the supremo over x, and this total variation distance, the supremo total variation distance, is bounded from above by the operator norm of St minus pi times 1 over pi star, where pi star is the minimum of pi. So this makes sense if for a finite Markov chain, for an ergodic finite Markov chain, where this quantity is actually strictly positive. So this is one way of obtaining information about convergence in total variation. Another way is to use the convergence in entropy. So it is customary to define the relative entropy between two probability measures in this way, just that pi of mu over pi log mu over pi. And if one is able to obtain good bounds for this quantity, so again the supremum over the initial condition of the relative entropy between st delta x st with respect to pi, then one can use a classical inequality test. I think is known under several names. I call it the Caesar inequality, that tells you that this relative entropy actually dominates the square of the total variation distance. So again, if you're able to find estimates for the relative entropy, then you get estimates also for the total variation. So this is just a little reminder about very basic facts. So having established that this L2 convergence or the convergence in relative entropy can be useful to estimate total variation, so let's study these two modes of convergence and let's see how we can get information about convergence with respect to those modes. Of course, also for this problem there are many approaches, but one of the most popular is by functional inequalities. So there are the convergence to zero of this quantity correspond in a natural way to some classical functional inequality. So before being able to define these functional inequalities, I just define some more objects. So the first object is the Dirichlet form. So the Dirichlet form is a bilinear form which is defined as minus the expectation with respect to equilibrium of f Lg. L, remember, is the generator of the process. And, well, in the case the chain is reversible, I will actually assume in most of this talk reversibility. By reversible, it means that, for instance, these conditions are true, holds true. The intensity of jump from x to y times the probability of x is symmetric in x on y. These are the detailed balance condition. In a more abstract way, this is equivalent to say that the L is alpha joint in a 2 of pi. And in this, under this condition, the Dirichlet form is actually a symmetric bilinear form and can be given in this way. And actually this formula that will play some role in the rest of my talk is actually true for f equal g, so on the diagonal, even without reversibility. So this is strictly true for any fg with under reversibility, but it is true for f equal g even without reversibility. So another notion that I will introduce, so we have the relative entropy between two probability measures. Then I define now the entropy of a function with respect to a measure. It is defined in the following way, and there is an obvious relation between entropy of a function and entropy between measures, in the sense that the entropy, the relative entropy of mu with respect to pi is just equal to the entropy with respect to pi of the Radon-Nikodym derivative. So all this is straightforward, essentially obvious. Okay, these are just notations, and so now let's go to the point where functional inequalities come up. So there is this theorem that the statement that the L2 norm, the operator norm of st minus pi is bounded by an exponential function e to the minus gamma t with gamma positive, of course, it is equivalent to the validity of the so-called Poincare inequality, which in this context states that the variance of f with respect to pi, which is of course this, is less or equal than 1 over gamma times the Dirichlet form on the diagonal, and this has to hold true for every f. So this constant gamma does not depend on f. And it is known that the best constant, the best gamma, so the largest gamma in the Poincare inequality is nothing else than the spectral gap of the symmetrized operator L. And in a totally analogous way, you have that the exponential decay of the relative entropy, so the fact of having a positive constant alpha for which the relative entropy decays in time exponentially with constant with rate alpha, is equivalent to this other inequalities that states that the entropy of a function f, the entropy is defined only for positive function, is less or equal than 1 over alpha times the Dirichlet form, now not computed on the diagonal, but off diagonal in the element f log f. Okay, this inequality, as Prasad mentioned Monday, has been sometimes called entropy inequality. Actually, I used to call entropy inequality. I think the name modified logarithmic Sauer inequality has prevailed in the time, so I will call it modified logarithmic Sauer inequality, even though there are other modified logarithmic Sauer inequalities in the literature. So this is not by no means a name that really identifies this precise inequality. So I just give this name for this talk to this inequality. So you see there is a very natural link between these two functional inequalities and exponential converges to zero. Exponential converges in equilibrium with respect to these two modes of convergence. So in particular, if I do have the Poincare inequality with constant gamma, then I have the bound in the operator norm, so I can use the connection with total variation, and I have this bound on the total variation. So the total variation is decaying to zero with this rate. While if I use, instead of Poincare inequality, I use the modified logarithmic Sauer inequality with constant alpha, then what the inequality together with Caesar inequality would give me is this bound in total variation. So you see I have a prefactor, which also depends on pi star. Remember, pi star is the minimum value of the equilibrium measure. And then here I have, again, exponential convergence. So which one of the two is better? Well, that depends on t. Depends on t because actually it turns out that it is always true that alpha is less or equal than 2 gamma. So as far as the exponential rate is concerned, this second inequality cannot be the first one. However, you see that if your chain lives on a state space which is big, pi star is going to be small necessarily. And so the log of 1 over pi star is much, much smaller than 1 over pi star. So this prefactor is typically much smaller than this prefactor here. So for moderate times, this inequality could be much better than this one. For example, suppose that I want to estimate what it is called the mixing time. The mixing time is, for instance, the first time for which this quantity is below 1 over e, for example, or 1 over 2. And then, of course, it is usually much better to use this inequality to give upper estimates for the mixing time because of this prefactor. Having mentioned these two functional inequalities, I think it is also, I think I also have to mention even more classical functional inequalities, which is the logarithmic Sauer inequality. And I denote by S the constant in the best constant in the logarithmic Sauer inequality. So entropy less or equal than the Dirichlet form in square root of S, square root of F. Well, I think most of the audience here knows what is the meaning, what are the consequences of the logarithmic Sauer inequality, like hypercontractivity and concentration properties and so on. I will not deal with this specifically with this inequality in this talk. I just want to mention the fact that if you are in the continuum and you take a diffusion process, the modified logarithmic Sauer inequality and the logarithmic Sauer inequality are the same inequality, so there is no difference. and the difference between the two comes up in the discrete setting. So this inequality, the modified logarithmic inequality that I stated actually is relevant only in the discrete setting. So now we have these three inequalities, and the very classical result is, the fact that there is an ordering between these inequalities, which essentially states that the logarithmic sovereign inequality is stronger than the modified logarithmic sovereign inequality, which is stronger than the Poincaré inequality. For finite Markov chains, this means that the best constant in the inequalities are all positive and they are ordered in this way. But if you take a Markov chain with an infinite, for instance, a countable state space, then you see that, one inequality, each one, for instance, log Sobolev is strictly stronger than the modified log Sobolev, which is strictly stronger than the Poincaré inequality, in the sense that you can find examples, actually very natural examples, random walk on the positive integer, for example, birth and death processes, for which you have a strictly positive spectral gap, okay, so the best constant in the Poincaré inequality, but zero constant for the modified logarithmic sovereign inequality, and so zero also for the logarithmic sovereign inequality, or strictly positive gamma, strictly positive alpha, but zero s, and so on. So you see that it is a strict ordering actually already in the case of countable state space. So this is just a very basic introduction about this functional inequality. So one of the questions that naturally come up is so how you find these constants for the functional inequalities. So these constants are useful because then you get estimates for the rate of convergence to equilibrium. And so how to find, say, in specific models, maybe not the best constant, but good estimates for those constants. So there are several methods that have been developed. One of the first, I think, is what I refer to as a path or geometric method, which I think was first developed by Saloff-Coste, and then even more results are being established by Cyril Roberto. This method is beautiful to use, sometimes easy to use to get rough bounds. Sometimes when you deal with specific models, these models have parameters. For instance, one parameter of the model may be the cardinality of the state space. And so if you have a sequence of model, which depends on increasing state space, you would like to get the right scaling of the constant with respect to this parameter, for example. And with this method, sometimes this is kind of hard. So maybe not the best method to get the right scaling of the constant of the best constant in the functional inequalities. Another method which has been developed since I think the end of the 80s, first by Strug, Zegarlivsky, then Yao, Martinelli, Ondivieri, and many other, and I apologize whether I'm forgetting some relevant names in this list. This method actually is relevant for models with a spatial structure. So suppose that you have not only you have a time evolution, but the state space is, for instance, a product space. It's something which has a structure also in the space. And these methods try to relate the mixing in time of the process, so the rate of convergence to equilibrium, to mixing in property in space of the invariant measure. So if the invariant measure, say, mixes fast enough in space, then also the corresponding dynamics, Markov dynamics, mixes fast enough in time. So this is the rough idea. This is the results in this direction are very deep, in my opinion, and they are the method is quite powerful. However, to establish functional inequalities, for example, log Sobolev or Poincaré inequality, you need to prove spatial mixing, and this maybe something hard to prove for many models. And then the application of this method to inhomogeneous models, so models with a spatial structure but which are somewhat inhomogeneous in space, and I will show later an example which should reveal what I mean by inhomogeneous, have been proved to be problematic. When you have some inhomogeneity, these methods which relies usually in an induction in space is very delicate, so it's not very robust in this respect. Another method which is more recent for this function inequalities is what is called the Lyapunov function method, which has been developed by the Toulouse school, so Catio and Guyen mainly, but also other. And so this is very natural. I mean, it essentially says if you have a good Lyapunov function for your system, then there should be a fast convergence to equilibrium. So of course you have defined properly the notion of Lyapunov function in a stochastic setting, but this is something not difficult to do. And so it is very natural. I like very much this method. It is, however, again, the effectiveness of this method in models with a spatial structure is still unclear to me. So it's not, it is not clear whether this method can effectively be used, for example, in models as the one that I will present you in a few minutes. Okay, so this is only an overview of the various approaches to functional inequalities. So, of course, I'm here to propose mine. The approach I proposed is very strongly inspired by the work of Bakri-Emery in the 90s, which was also inspired by the previous work of Bochner, and of course, I mean, these works of Bochner, Bakri, and Emery, I mean, is very mainly it is a work which mainly concerns second-order operators, and it has many consequences. The results of Bakri have many consequences which go far beyond the convergence to equilibrium of Markov processes. They have consequences in essentially of geometric nature, such that curvature inequalities and things like that. So I'm not really going as deep as Bakri-Emery have gone. I'm just taking a little corner of their theory and try to extract and do something similar in a discrete setting. So that's what I will be doing. So let me describe a little bit what are some of the principles of this approach. So the first few things are really totally abstract. They do not have nothing to do with the specific setting, discrete or continuous, you are working in. So remember, the fact I stated before a theorem that was saying that you have exponential convergence to equilibrium in L2 if and only if you had the Poincaré inequality. So what is the proof of this theorem? This is a very simple proof. You just take this variance here, the variance of STF. ST is the semigroup, and you take the variance with respect to pi, and you differentiate along the semigroup. And if you take the derivative, you get the Dirichlet form. So you see that what the Poincaré inequality does, what the Poincaré inequality does gives the possibility of closing this identity into a differential inequality for the variance. And so use then the Gromov lemma, and you get the exponential convergence to zero of the variance, which is essentially what gives you the exponential convergence to zero of the L2 in the L2 sense. But instead of just taking the first derivative, let's take the second derivative of the variance. Okay, this is an exercise. You take so minus twice the derivative of the Dirichlet form, and what you get is for the mean of this L applied to STF squared. Okay, this is a very simple result, and I forgot to say that this formula is strictly true under reversibility. So I work up under reversibility, otherwise there are other terms that come up, and I don't want really to deal with those terms. Okay, now let's take this last inequality. So the inequality which connects the identity, which connects the derivative of the Dirichlet form with this other object. And suppose that we want a functional inequality that allows to close this identity into a differential inequality. So essentially the inequality that we are looking for is this one. The Dirichlet form in FF is bounded from above by some constant 1 over k times pi of LF squared. If we have this inequality, then we can close this identity into a differential inequality, which is this one. Okay. Just remove the first term, I just looked at the second term. So which is this one. Of course, this implies the fact that this Dirichlet form converges to 0 exponentially. So if there is a minus here.
No, in the middle form.
Here?
No, one second. Yeah, the second equality. I guess it's a plus or a minus, but which one?
Let me see. This is a minus, and there is a plus here. This is a plus. Yes. Yes. This is saying that the variance is going down in a convex way. Okay. The second derivative is positive, so plus is correct there. Okay, so let's go on. So we have, of course, that this goes to 0. So we can rewrite this inequality, the inequality that we have obtained in this way here, by using the fact that the derivative of the variance has been computed before, and we integrate this from t to infinity, and we get this. And as you get this, but this is just the Poincaré inequality. So what we have obtained is that if we have a constant k for which this inequality holds true, then k must be less or equal than the spectral gap. So it gives a lower bound for the spectral gap. Indeed, a bit of spectral theory shows that the best constant in this inequality is actually equal to the spectral gap. So the two inequalities are equivalent, not for a single f, but for, one inequality is true for every f if and only if the other inequality is true for every f. So I call this inequality pi prime, so this is an alternate form of the Poincaré inequality. So let's try to do the same. So this little game of taking the second derivative for the entropy. So if I take the second derivative of the entropy, of course, by the first derivative of the entropy you can repeat the same argument for the variance for the entropy, and you get the second part of the above theorem. So that the exponential decay of the entropy is equivalent of the modified logarithmic over inequality. But let's take the second derivative of the entropy. Now, taking the second derivative, we get something a little messier than what we obtained for the variance. So we obtain something less pleasant, but let's accept that. And we do the same thing. We try to design a new inequality, which essentially is saying that the derivative of the entropy is decaying exponentially. And the inequality that does the job is this one. K times the Dirichlet form in f log f less or equal than this sum. And it turns out that if we have a constant k for which this inequality is true for every f, then we have the modified logarithmic over inequality for the same k. There is this implication. So this inequality is at least as strong as the modified logarithmic over inequality. One say it is more complicated, so why one should take this inequality? So this is what I will try to convince you later. But this time, this inequality is not equivalent to the modified logarithmic over inequality. Again, this inequality implies not only that the entropy is going down exponentially fast, but it's going down with a positive second derivative, so in a convex way. Okay? And while the variance, if the variance decays exponentially, necessarily decays in a convex way, This is not true for the entropy. You can make up examples in which the entropy decays exponentially, but not in a convex way. And so models for which the modified Log-Sober inequality holds true, but not this MLS prime, this further modified logarithmic Sober inequality. So this inequality is strictly stronger than the modified logarithmic Sober. So besides being more complicated, it is harder to establish because it is stronger. So why should we take this inequality? So
Do you know some conditions under which you can show if the equivalents are up to some constant?
No, I never thought about that. I mean, typically you have to introduce some sort of inhomogeneity in order to see that, to find those counterexamples, but I really don't know. Okay, now here is the following. So we would like to study this inequality in a discrete setting. So I would like to develop a language which cover most of the examples I do have in mind about Markov chains and Markov processes in finite or countable space. So I suppose suppose that the generator can be written in the following form. So I have a state space X, and then I have a set G of functions from X to X, which I call the movements, the allowed movements. I mean, the idea is the following. The dynamics is of the following way. So I have this set of functions, and I have my state space, and suppose that my current state is X. Then I pick at random, with some law, an element of G, and I apply this element to X, and I get the next state. Okay. So this is the dynamics. Of course, it is a continuous time dynamics, so the waiting time is exponential. And so this Cx gamma is just the probability rate of picking gamma if your current state is X. Okay. So this is a way. And if you think about it, any finite Markov chain can be written in this way, and essentially any decent discrete process can be written in this way. So this is a way where you can write processes in which the evolution is just by jumps. Okay, of course, I wanted to describe a process which has pi, a given pi as an invariant measure, and more than that, I would like pi to be reversible. So I have to give conditions on these rates in order for reversibility to make sense. But of course, for reversibility to make sense, it means that if I have a movement, I also have to have an inverse movement in some sense, for just to define reversibility. So I essentially give this condition. If I have a movement gamma, there exists an inverse movement gamma minus 1, which is not really strictly the inverse as function, but satisfies this condition. Gamma minus 1, gamma of x is equal to x for every x such that the rate is strictly positive, but forget about these details. And then the detailed balance condition, which is equivalent to reversibility, can be written in terms of this gamma and gamma minus 1. So there is nothing mysterious here, just the usual detailed balance condition in this language. So just to convince you that it can be written in this language. Okay, now this is really a horrible slide. And what I've done here is just to write the inequalities pi prime and MLSI prime, so those modified inequalities, in terms of this sort of generators. So what is my point here? So look at the first, this is the pi prime. So you see that what appears in both sides of this inequality are means, with respect to pi, of quadratic forms in the gradient gamma. Remember, the gradient gamma, I did not say, but I defined here. The gradient gamma of a function is just, of course, a discrete gradient. So in a sense, why is this nicer than the Poincaré inequality? Because for the Poincaré inequality, you have this on one side, on the other side you have the variance. The variance is a quadratic object, but not in the gradient, it's a quadratic in F. So by looking at these alternate inequalities, you can think you can get away by using some comparisons of quadratic form. So this is the idea why this may look a little better. Of course, if you look at what is the MLS prime, then this is certainly not encouraging, because it is true that we have only gradients, but I mean, these are not, this is not the quadratic form in the gradient of f, because it appears also the gradient of log f. So let's look back to the first inequality. You see here we have a diagonal quadratic form. In terms of the gradient, this is diagonal. This is, of course, not non-diagonal. This has many non-diagonal elements. So how to compare these two forms? So let's concentrate first on pi prime. And, okay, I'm not really explaining you a theory, in the sense of something which has really a very nice development, and you understand all the steps. So there is something magic and something that I do not really fully understand, but that works. And so, in a sense, I'm not able to justify properly all steps that I will show you. What I wrote here in the blackboard is just to have as a reference what happens in the case in which you have a diffusion on a manifold, on a Riemannian manifold. So your generator is a second order operator. So this is the Laplace-Beltrami operator on the Riemannian manifold. And then the pi LF square is this object here, is equal to the sum of two terms. The first term is a positive, say, quadratic form in the Hessian of the function. And then you have, this is the Ricci tensor, this is the Hessian of the potential V. These are bilinear forms applied to the gradient of f. So we would like to have something like this. Because why is this useful? Because this is useful because in order to bound from below this term here, which is what you need to establish the pi prime, you can essentially throw away this, because this is positive, and you can, I mean, for instance, if the space is flat, so if there is no curvature, you can get, for instance, the Poincare inequalities just by having some lower estimates for the Hessian of the potential. Okay. This is what can be done in the continuous case. And we would like to reproduce something similar. However, so what is the metric tensor in this context? What plays the role of all these objects in this context? I don't know, but I can propose something. So look at this quadratic form. So this is pi of LF square. This quadratic form. So we can modify it as follows. So to fix ideas, suppose that you are in this specific case. Your invariant probability is of the form 1 over z e to the minus h. So it is sort of Gibbs form. And suppose that you choose the rates in the following way. The exponential of minus the gradient of h divided by 2. These rates actually satisfy the detail balance. It's easy to check. And also assume that your movements commute. This is another condition which is not always true in the example, but to fix ideas, suppose that all these things are true. Then take this quadratic form and replace in the second occurrence of the rate of the intensity c, replace this x by gamma of x. So instead of writing cx gamma, cx delta, I write cx gamma, c gamma x delta. So I move this second x. And then what happens is that this object here is something that resembles this object here. It's something positive which contains squares of the second derivative. So this is equals, this is a two-line proof, equal to the same coefficients, and now you have the second derivative, discrete derivative squared. So you have something positive, something that resembles the Hessian. And I mean, the proof of this identity only requires the usual reversibility and nothing else. So what does that mean? Well, it means that so our point is to prove pi prime. We have to bound from below this object. So if we bound from below this object minus this, we are done, because this is positive, we are doing even better. So this means that if we can find a positive constant k, such that the Dirichlet form, which is this, is less or equal than 1 over k times this is the difference. Instead of writing only cc, I write cx minus cx c gamma x. Well, I'm getting something even stronger. So why should this work in any way? So I don't know. It works. The only suggestion I can give you is the following. Suppose that you have a model which has a spatial structure. Okay, so you have a space, and suppose that your state x is a configuration in space. So suppose it is some profile in space, and any movement, what a movement does is to change your configuration only locally in space. So it modifies the profile only locally. So suppose that you take two movements, gamma and delta, which acts in far apart region in space. And suppose that your dynamics is also local. So the rate at which you apply gamma does not really depend on all configuration x, but only on some local region closer to the region where gamma acts. So it means that if you transform x by gamma, it means that I'm transforming x, changing x over here, and then I apply delta. Delta works over there, very far away. Then this rate here does not change if instead of x, I write gamma of x. So if the fact that I change the configuration in some region of the space does not change this intensity, which refers to another movement that acts in a very far away region of space. So these two rates may be equal if gamma and delta are sufficiently far apart. So in a sense, this difference is able to eliminate many non-diagonal elements in this quadratic form. And since we are going to compare this form with the diagonal form, quadratic form, this is useful. This is about the only intuition that I can give you. Okay, this is essentially what I said. Of course, I mean, this perturbation of the form by subtracting Cx, C gamma x works because I chose the rates in a specific way. In general, how do so I have my product of the rates and I want to change it by some additive factor and to get another thing. So to transform the quadratic form from this one to this one with this gamma r. So this gamma r is this gamma r are the coefficient of the quadratic form in which this product of the C is perturbed by some r. And in order for this replacement to work, R should satisfy a certain number of properties, which are essentially symmetry, something which says that if you fix delta, R has to satisfy the tail balance condition with respect to pi, and then there has to be some sort of commutativity of gamma and delta whenever R is 0. So R is a positive function. So I think you can really skip these details. So there is a way which is non-unique, by no means unique, of perturbing the quadratic form and to obtain this inequality. So the quadratic form, which is pi of LF square, is bounded from below by another quadratic form. And if you write, I mean, the reason why this inequality is true, you get this identity. Pi of LF square is equal to this term plus a term which contains only square of the second derivative. So what I claim is that this has some similarities with this identity. Okay, so this gamma r, in a sense, are the right coefficients to fix, to have an analog of this identity in this discrete setting. As I said, R is by no means unique. the fact that, because then you see, what you do is you throw this away and you try to bound from below this by a multiple of the decay form. The fact that you succeed depends very much on the way you choose R, and so since it is not unique, this is not really I have no canonical way to choose R, and so I have no really canonical object for replacing this curvature metric tensor. Yes.
But in spite of that, let me ask, where do you suspect that Ricci might be hiding?
I'm not suspecting that at all. I really don't. Frankly, I don't see it. Maybe to see it, you should really take, you know, random walks on graphs, and I mean, one should really work out specific models which resemble, I mean, the diffusion processes, and maybe you can find something. We have not really tried that, actually. So this would give some geometric interpretation of these objects. So our aim was just to use this to prove, to give estimates for the constants in the function inequalities. Okay, what I found surprising is that if you do the same replacement, product of C with gamma R, in those terrible objects that appear in the MLSI prime, then this inequality is still true. Okay, I frankly don't understand why it is so. I mean, I can prove that, but I mean, this really is robust. When you have this, I mean, no matter if you have these strange objects, I mean, this is still true, and there is, so Bakri-Emery developed the analog for the modified, for the logarithmic sober inequality of this inequality. In a sense, this is our discrete analog of that, and it exists with the same type of perturbation. It is not?
But it's not non-negative.
No, the difference between the two is non-negative. So what is missing here is the other positive part, which should be something like this. It is not so obviously positive, but it is positive. Okay, summing up, it means that once we have decided what good R is, if we can establish this first inequality, then we have the Poincare inequality as an outcome. And if we establish this apparently terrible inequality, we have the MLS prime inequality as an outcome. And of course, this implies MLSY. So this is a not very straight path to obtaining the inequality. And in the last minutes, I just would like to show you an example in which this works. I mean, I still think it is amazing. I mean, this works, this idea do not work always, of course, but it is remarkable that it works in many examples. What is the, how did we pick these examples? Our idea is to take systems in which the state space is a product, is a Cartesian product, so this is a spatial structure, and so it is a space of a certain dimension, and the idea is to get conditions for which the best constant in a functional inequality do not depend on dimension. Okay, so do not depend on the space, on the cardinality of space. So let's see this. Suppose that you are on the lattice ZD and take a finite subset of ZD. Lambda is a finite subset of ZD. So this is our space. And then take k and lambda, two positive functions, two non-negative functions, k0 equals 0, and k is summable and lambda is bounded. And then I take the configuration space X to be n to the lambda. It means that to any point of lambda, I put a certain number of particles, say. So, sorry if it is a little messy. Now X, now the configuration is denoted by eta, and X is a point of lambda. so it's not a point of x. So x are the sites, the points, the discrete points in space, and eta denotes configuration. So eta of x denotes the number of particles which sit at x. So I take this pi, I choose a pi first, a certain probability on this space. So what is this pi? Suppose that I remove this exponential factor. So in this case, this pi would be just a product of Poisson probability measures on each site. So it means that at this site I have Poisson distributed, a number of particles which is Poisson distributed with mean lambda of x. When this mean can vary, is not homogeneous. So this is a kind of inhomogeneity that I was mentioning before. The mean number of particles depends on the site. And then I perturb this product measure by introducing some interactions between number of particles at different sites, and I use this pair interaction, which depends on this k. And beta is a parameter which has the interpretation of inverse temperature. Okay, so this is the pi. What are the allowed movements? The allowed movements here are either you create a particle at a given site, or you remove a particle at a given site. So these are the only movements that you can allow. So gamma x plus means I add a particle at x. Gamma x minus means I remove a particle at x. Of course, if there is no particle at x, I do nothing. Now I have to pick up rates for which I get a reversible Markov process with respect to pi. So I remove particle with rate at x with rate eta x. It means that any particle is removed independently of the other with rate 1. Okay? And then once I fix this death rate, the birth rate is somewhat fixed because it has to satisfy the tail balance. And it turns out that the correct birth rate, the creation rate, is this one. It's lambda of x multiplied by this exponential factor. Now I choose R. So essentially, suppose that I choose R of gamma x plus gamma y plus. So as I was saying before, one possibility, the canonical possibility, is to choose R to be the product of the two intensity, but where the second intensity is changed by applying the first movements. So instead of writing C of eta gamma y, I write here C of gamma x plus eta gamma y plus. This is what I do. I do the same for the minus maps. And then, I mean, this so mixed R with the creation and annihilation is not of the same form. It has to be this, because otherwise, this is somewhat forced in order to satisfy the condition that I prescribed on R. So just believe me that this R satisfies the properties that I was mentioning before. It's a little less messy to write delta x plus minus instead of delta of the creation and annihilation movements. So let's take this R, and let us use the above ideas. So I have this pi of LF square. I saw that it was greater or equal than what I got with a gamma R. So let's see what gamma R is. Okay, I just make some computation. What I get out of this gamma R is the following. Notice that before of the fact that this R on the mixed movement is equal to the product of the C, in gamma R I do not get anything which depends on product of gradients, one gradient plus, one gradient minus. So I get either two gradient minus or two gradient plus. For the gradient minus I get only this term here, which is actually equal to the Dirichlet form. By reversibility one can show that it's equal to the Dirichlet form. And then I have this one, this term here. Now look at this term here. So remember k is positive, so this is a 1 minus this is positive. And I have this non-diagonal form in the gradient. So I would like to reconstruct the Dirichlet form here. I could reconstruct the Dirichlet form if I could remove one rate. I could remove this factor, and I could have only gradient x, gradient x. In this case, I would reconstruct the Discrete form. So how do I get rid of these products of gradient x, gradient y? Well, this is really deep mathematics. Twice the product is greater or equal than minus the square, the sum of the squares. So this is really the only ingredient here. If I use this deep inequality and the fact that the rates are bounded from above, then I reconstruct here in a very simple way the Discrete form, and I get this result. I get that pi of Lf square is bounded from below by this quantity here times the Discrete form, where epsilon of beta is the sum over x of 1 minus the exponential of minus beta k of x. So of course this is a good bound if lambda bar, epsilon, lambda bar is the supremo of the lambda x, is strictly smaller than 1, of course, because I mean, if this is negative, this is just useless. When essentially when epsilon of beta is small, but epsilon of beta is small when beta is small. Actually, epsilon beta goes to 0 as beta goes to 0. So this is a high temperature condition. So since beta is the inverse temperature, for small beta, this is a positive constant. And we have this bound. Now, essentially, this is the proof. This is a one-slide proof, so half-page proof. And this is a proof, this result was actually proved by Bertinic and Crinichesi in 2002 with a totally different method under the same conditions, actually with a slightly worse lower bound, but just really a detail. And it was reproved by Kondratiev and Litvinov in 2005, essentially by the same method that I showed you. So in a sense, even though it is very rough what we are doing, really we are acting by brute force, I mean, the result that we have obtained is not worse than the best available results in the literature. Now, last 5 minutes. Can we establish stronger inequalities for this? For example, modify logarithmic over inequality. Well, certainly, it is known that for this model, the logarithmic over inequality does not hold true. Even if you take just one birth and death process, which is reversible with respect to Poisson, it is known that the logarithmic over constant is 0 for that model. So LSI is hopeless. How about the modified LSI? So you see, what was the key step in our proof of the Poincaré inequality? It was this. The non-diagonal term in the quadratic form were replaced by diagonal terms by this terrible inequality. Of course, one can say, okay, but one can do much better than that, because this is just an instance in which you want to bound a symmetric matrix from below by a diagonal matrix. And what we have, if we use this inequality, we are just using these bounds, that these bounds hold true if I take as a diagonal elements of the diagonal elements of A minus the sum of the non-diagonal on the same row. So this is certainly not typically the best estimate from below of a symmetric matrix. Nevertheless, this has worked pretty well for the above example. So now suppose that I take MLSI. What do I get? Just look here. Well, first of all, I get the Dirichlet form, which is what I want to have, because this has to be bounded from below by a constant multiplied by this. Then I get this, which is a positive object, so good. If it is positive, I can throw it away. And then I get the non-diagonal terms with the plus gradient. But of course, there are the plus gradient and the plus gradient of the log of f. And so what we thought, okay, we thought that there must be an inequality telling you that grad y of f, grad x of log f, maybe in absolute value is less or equal than a constant time the sum of the diagonal term, grad x f, grad x log f, plus a constant, grad y f, grad y log f. This is what I thought. There must be something that works in this way. Well, if you write it down, you see that there is no constant that makes this job. It is false for every constant. This inequality. So we have been stuck for a long time to this. And the idea is that you cannot throw anything away here. You cannot throw away this positive term. You cannot throw any, you can keep everything. And essentially the point is that now this inequality that was the right inequality for the Poincaré inequality is now replaced by this inequality. So in a sense, for those of you who already know a little bit of my results, this is the only new ingredient, new result that I have. It is this inequality for a function of two variables. And I mean, the proof of this inequality is totally trivial, but it took us a long time to find out that that was the right inequality. And what does this inequality do? Essentially, if you take this gradient x, gradient y, f log f, together with the other terms, with the gradient divided by f, then you can replace all of them by purely diagonal terms. And all these diagonal terms match, and I conclude very fast, and all of them match. Sorry, this is certainly not a readable slide. And as an outcome, what do we get? We get the modified logarithmic sovereign inequality. Sorry, there is a lambda bar missing here. So with the same constant as the Poincaré inequality under the same condition. So you see, I mean, although we are doing something extremely rough, after all, I mean, at least in this example, this is not so rough. We really get the modified logarithmic sovereign inequality, which, as far as I know, was not proven for this model before, by a very simple, I mean, by a one-page proof with the same condition as the Poincaré inequality. Okay. This is somewhat surprising. Of course, these conditions are not optimal. The constants are not optimal, but still they are lower bound, which are independent on lambda, on the dimension of the space, for example. So they are really uniform in lambda. And so we have this is the theorem. Okay, I just now conclude. Just very briefly. As I showed you, for this model, the way we obtained the Poincaré inequality was by using this very naive lower bound of a symmetric matrix with a diagonal matrix. Essentially by using this AB smaller or equal than 1/2 a squared plus 1/2 b squared. That was the only ingredient. Sometimes you can do much better by giving estimates on the spectral radius of the matrix of a quadratic form. There are models, for example, the loss network representation for Pire's contour, which I have no time to describe, for which this approach works well for the Poincaré inequality, but you cannot use this brute inequality for estimating from below the quadratic form. You really have to use more sophisticated bound on the spectral radius. And so there are cases in which this, say, local estimate do not work. You really have to look at the whole matrix and to bound it from below properly. And these global lower bounds for the logarithmic sovereign inequality do not work. So the only thing we can do is you take one specific non-diagonal element and bound from below by a sum of diagonal elements. So we cannot take all them together and get and have best constant out of that. So this is something that we have not been able to do yet for this approach with the modified logarithmic sovereign inequality. Okay, thanks a lot.
Questions? Is there a possible comparison between Dobroshin uniqueness condition and MLSI, even in the birthday case, in dimension 1?
What do you mean the Bruching uniqueness in dimension 1? Sorry,
Yeah, it's a version of Yann Olivier's Ricci curvature.
No,
for example,
no, I don't know. I was thinking of the Bruching condition as the condition for Gibbs measure, which implies analyticity, and this condition is very much related and to logarithmic solving inequalities, for example. But no, the type of condition you are mentioning, I don't know, so I cannot answer.
Where in your argument was it important that K is positive, that the interaction is...
The K, okay, for this proof, I have this, say, repulsive. K positive means that you are discouraged to put too many particles together, and well, if you allow K to have negative values, well, on one hand, there may be problem in having the infinite volume limit of the process. Why for K positive there is a well-defined infinite volume limit, but nevertheless we are not using here the infinite volume limit. The specific argument I showed actually used the fact that K is positive because our inequalities that was replacing this one for the non-diagonal element was only a one-sided inequality. Okay. So in order to deal with K that may be negative, we need a two-sided inequality, which is not actually hard to establish. There is a two-sided inequality that we have tested. I have not tested with this model with K negative. I have tested with models because with K negative, the fact that the number of particles here is unbounded can become problematic. I have tested, for instance, for the Glauber dynamics for an Ising type model in which you have spins, not the number of particles is either 0 or 1, say, and then you can really get away with the ferromagnetism and prove a high temperature condition without any ferromagnetism.
Does the method also allow to recover some other modified logarithmic Sobolev inequalities, like in the symmetric group, the result of Wastel-Gau and Prasad? And
okay, we have we have used this method for let me think about the Laplace-Bernoulli model, the Bernoulli-Laplace model. And I think we failed to use it for instance the transposition model. If it is, I think we cannot do it. So there are still essentially this method so far works very well when you have birth and death processes. So Glauber type dynamics. When you have sort of exchange dynamics, it is much more delicate, and so it works in certain examples. For instance, for Kawasaki it works, but if you have more sophisticated models, it is still we still do not succeed in applying that. So we do not really recover that result.
Actually, so something strange, how magic happens. So in Gauss-Pastel, they have both Bernoulli Laplace and symmetric group transformation. Pietro we tried with this approach, and things cancel out very nicely for Bernoulli Laplace, but it doesn't work for them. The distinction is unlabeled particles versus labeled.
Yeah, that's label against versus unlabeled seems to be really a key point.
Questions? If not, let's send the speaker again.